Before we actually start applying the derivative, we want to take a look at making a connection between the graphs of models and the derivative itself and what information we can pull from that. So let's look at a few graphs here and see what we can figure out. Let's look at all the different things that we can say about this graph. First, let's talk simply about the slope. Here we have a positive slope or an increasing slope. Our first derivative is our slope, so this is when our first derivative is going to be positive or when it's going to be greater than 0. So anytime we can find the x values where the first derivative is greater than 0, we know that our slope is increasing. Likewise, over here we have a first derivative or a slope that is negative or decreasing. We have another area of positive slope or increasing, and we have a final area of a negative slope or decreasing. And so if our slope is less than 0, we know it is decreasing. If the first derivative is less than 0, we know we have a decreasing slope. Now, in between the increasing and decreasing, we have points at which our tangent line has a slope of 0. So this is when our first derivative equals 0, and that is when we're either going to have a maximum value, or in this case, a minimum value. So maximum values and minimum values, or what are called optimal values of a function, are where the first derivative equals 0. Also remember that there are times when we don't have a derivative at all. So in this one, our first derivative does not exist. If you remember back to Unit 1, it had to do with the teeter-totter effect. But we do have a maximum here, and so the maximum can also occur where the derivative does not exist. There is one other place that minimums and maximums can occur, and that is at our endpoints. So when we talk about optimizing our function or our model, we are going to be looking at when did we maximize our profit, when did we minimize our cost, and those take place in 3 different locations: where there are endpoints, where the first derivative equals 0, or where the first derivative does not exist. Now there are 2 types. There's what's called the local max and the absolute max, and likewise local min, absolute min. This guy over here is going to be our absolute max because it is the highest maximum of everything. This other max is what is called a local max because it is the highest point in that area. Likewise, this endpoint would be a local min. This endpoint would be an absolute min because it is the lowest point on our entire graph. But this minimum here would be a local, and this endpoint would be a local min. So absolute means it's the highest for the entire function, and local means it's in that area. Now, then the question is, how do we know if something is a maximum or a minimum? So notice that the max and the min can both occur when the first derivative equals 0. There is something called concavity, and so concavity is the idea of, is that function turned down at the point or is it turned up? So this area is called concave down, and this area is called concave up. And the point at which it switches from concave down to up and vice versa is called the point of inflection. And that is where it changes. The point of inflection has to do with when the first derivative does not exist because it is a vertical asymptote. It is also where your second derivative equals 0. And we'll summarize this in just a moment. I'll show you an example of the second derivative equaling 0. Concave down is, if you notice, what's happening is that our slope is flattening, and so therefore it is slowing down, which means the acceleration is slowing down. And remember, our second derivative is acceleration, so when it's less than 0, it's concave down, and when the second derivative is greater than 0, it's concave up. Point of inflection is when the second derivative equals 0. So the first derivative is telling us whether things are increasing or decreasing. The second derivative, or the concavity, is telling us whether it's doing that slowly or quickly. So is our profit going up or down is first derivative. Is it going up or down slowly or quickly is our second derivative. Alright, so that's that direction, or that information. And let me slide down to another graph here and talk about a few other things, and then we're going to fill in the summary chart. So here I just want to revisit the idea of concavity. Remember that where the horizontal line has a slope of 0, so f prime equals 0, we have ourselves a max, and we are going from increasing to decreasing. That's going to create a concave down, and that again is when the second derivative is negative. So when we check for how quickly it's doing its change, we're checking concavity. Over here we have a first derivative of 0. It gives us a min. We're going from decreasing to increasing, which gives us a concave up, which is when our second derivative at that point is greater than 0. And so we'll use all of these items in just a moment when we're looking at functions. Let me also revisit the point of inflection, because I kind of threw all that in. Notice on both of these, this one is concave up, going to concave down. And if you think about, if it holds water, it's concave up. It's a cup if it can hold even a drop of water. If it will dump the water, it's concave down. Okay. This one is concave down, changing to concave up. So both of these have a point of inflection. And let's look at the situation. Here, if we can imagine drawing a tangent line just at that point, this is where the first derivative does not exist. An example of that would be something like y equals x to the 1/3. If I take the derivative of that, I get 1/3 x to the negative 2/3, or 1 over 3x to the 2/3, and therefore x cannot equal 0. So there is a point here at x equals 0, which is where this point is located, that we do not have a first derivative, and therefore it does not exist, but it is a point of inflection. The other example, notice that we have a positive first derivative throughout. Okay, and yet we're changing from concave down to concave up, and if you were to draw a tangent here, it would be a horizontal, and so this is when the first derivative equals 0. So there's another situation when you could have a point of inflection, is when the first derivative equals 0. but notice that the slope is positive throughout the whole thing. Okay, so concavity and points of inflection are connected. The slope determines whether you have a maximum. So we had a max here because the slope went from positive to negative. But here at f prime equals 0, we had a point of inflection because our slope was positive the entire time, but we went from concave down to concave up. So it's all tied there together. Let's fill out the chart and then we'll use that to summarize with some examples. So remember that when we talk just about the actual function, that this gives us our actual data points or the point, or the points on the graph. So it tells us where we are. It answers the question, where are we? That's what a function does. The first derivative answers the question, how fast are we getting there? Okay? Or how, are we improving or not improving? Are we increasing or not decreasing? Remember, the idea of continuity is that f prime of x exists if we have a continuous function. Okay, so we're looking for the continuity of a function lends itself that there is a derivative. Remember, there are some exceptions where f prime does not exist, and that is when we have a cusp. Okay, so you have to kind of keep a look on all of those. The critical points are your maxes and your mins, or your points of inflection. So all of those are critical. Maxes, mins, which are called the extrema, occur when we have a change in direction. The point of inflection occurs with change in concavity. Okay. And no change in direction. Okay. So to see if we have a critical point, so to find the max, the min, or the point of inflection, number one, you check to see where the first derivative equals 0. Those are possible points of inflection. 2, you ask if the first derivative is undefined, because that again can give you a critical point. It can give you a max in the case of the cusp. It can give you a point of inflection in the case of a curve that doesn't change direction. And then you always have to check endpoints. So there are 3 situations in which you will find maxes, mins, and points of inflection. Remember, we said that when your first derivative is greater than 0, you have an increasing function, and this is when your slope is positive. If your first derivative is less than 0, you have a decreasing slope, or your slope is negative. So if you're trying to find out when the company's not doing well or when it is doing well, you can use the first derivative to find that. And now the second derivative. The second derivative helps us determine if it's a point of inflection. If the second derivative is 0, that is an indication that it is the point that you located is a point of inflection. So the first thing you would do is find your critical points. Then you want to test, are those critical points points of inflection? You would check to see if the second derivative equals 0. This is especially helpful if the first derivative is undefined. So especially when first derivative is undefined, you need to check that. Or it is possible that your second derivative does not exist at points of inflection. And back in those graphs, we looked at that a little bit. The concavity, if it is concave down, it is when our second derivative is less than 0, and when it concave up, this second derivative is greater than 0. So we can plug in a value or a point and find out whether we are concave up or concave down. If it is concave down, that means we have a max at the given point, because it would be at the upper side. If it is concave up, that means we have a min, because we have the lowest point there. So again, to recap, there are three things: function, first derivative, second derivative. Function tells us where. First derivatives tells us in what direction. Are we improving? Are we increasing? Are we decreasing? And the second derivative tells us how fast we're doing that. So are we slowing down our loss, or are we quickly growing? Are we quickly going in the hole? Are we going in the hole slowly, or are we going in the hole quickly? When we want to look at functions, we would locate function values by using the function. We would locate critical points by looking at the first derivative, and then we would locate concavity by looking at the second derivative. So let's do one or two examples in this video, and then there's another part 2 video that has a couple of more examples. So let's look at number 1 and 2 here. First of all, we have that y equals negative 4x squared. I hope that we're able to think about that graph, that it is a parabola and that it opens down, but let's use some information to also confirm that. Let's find our derivative, which would be negative 8x. And let's find our second derivative, which is just negative 8. And let's talk about what these different things tell us. First of all, let's talk about that second derivative and the fact that there's no variable. This second derivative will always be negative. If it's always negative, that means the entire function has to be concave down the entire time. If it's concave down the entire time, there can be no points of inflection because it's not changing concavity. And that means, since it's concave down, that we're going to have a maximum value at some point. So we can see a lot just by looking at the derivative. Now, the fact that y prime equals negative 8x means that it's going, when x is positive, the derivative is going to be negative, and when x is negative, the derivative is going to be positive. So for the positive x values, my slope is decreasing. And for the negative x values, my slope is increasing. And that kind of confirms our whole concavity argument. Now, where does it switch from increasing to decreasing? What we would need to do is take the first derivative and set it equal to 0. And so negative 8x equals 0. Solve for x. X equals 0. So at x equals 0, we have a critical point, and based on what we're seeing, we know that's going to be a max. And then if we want to know where that critical point is, we find f of 0 up here by plugging in 0. And so at 0, 0, we have a maximum. So this graph has to open down. We could pick more points if we wanted, but that's how that confirms that we have the correct graph as well. Now, we're not necessarily in this for the graphing, we're in this for understanding a function. If somebody gives me y equals negative 4x squared as a model for their company, then I know just by running the first and second derivative a lot about that company, and that's our goal of making the connection. Let's do the same thing with y equals 5x cubed. First, let's just take the derivatives. And so y prime equals 15x squared, and y double prime equals 30x. And let's talk about what these things are telling us. First of all, the first derivative, 15x squared, this one is going to always be positive no matter what the x is. And if the first derivative is positive, that tells me my slope is forever increasing. And then the question is, does that mean that we have a max, a min, or a point of inflection? Let's look at the second derivative. When x is positive, the second derivative will be positive, which means that that part of the graph is concave up. But when x is negative, the second derivative is negative, because a negative times 30 would give you a negative, which means it's concave down. So for the negative x's, we're going to be increasing as we go. So we're going to be going up from left to right, but we're going to be concave down. And then we switch to concave up. And so that indicates that somewhere we have a point of inflection. And let me jump back for a minute, because we didn't do one thing up top here that we should have done. And that is, we did not ask if the first derivative was undefined. Is there a point of something being undefined if it is negative 8x? And the answer is no, it's defined everywhere. So that did not give us another critical point. So let's do the same thing down here. First, let's ask where the first derivative equals 0. So we have 15x squared equals 0. Solve for x, and we get x is 0. So again, we have one critical point at 0. Let's ask if it's undefined at all. And the answer is no, because we can plug an x into everywhere. If we had a fraction or something, you would have to worry about that. So to find our critical point, we plug in 0 and get 0 again, and that's just mere coincidence because I was starting with some basic functions. So 0, 0 is a point of inflection because it's our only critical point. If you want, you can plug in 0 into here, and we should do this to confirm, but we've kind of justified it. But putting a 0 into the second derivative does gives us 0, which confirms a point of inflection. So we have a point of inflection. This function is increasing, so it's got to go up from left to right, but it's got to be concave down in the negative x's and concave up in the positive x's. And so knowing this information says to me this is a company to consider investing in, because it's going to always be improving. It's going to hit a slow area where it slows down a little bit when it switches from concave down to concave up. It's going to slow down its improvement a little bit, but then it's going to take off. And so understanding what those functions tell you, you don't necessarily have to graph, but it tells you, when I look at these two companies, I see that one is going to hit a max and it's going to be concave down forever. That tells me this company is going to have its good day and then it's downhill from there. Company number 2, if this is their profit model, they are always improving. They may have some slow periods or kind of plateau periods, but then they will continue improving again. So if I had to pick between company 1 and company 2, I think I'd probably pick company 2. So that's the basic idea of finding critical points, using concave up and using concave down to help you determine things about the company. Now let's just take a look at number 3, and that is that sometimes it's difficult to do the critical points because things are undefined. Let's take a look at the graph of f of x equals 1 minus the absolute value of x. And if you're not familiar with absolute value graph, you can throw this in your calculator, but absolute value graph is a V, and the plus 1 here is going to move it up 1. The negative is going to flip it down. So if this is a 1, the absolute value graph looks something like this. Now, we can't take the derivative of the absolute value, and the reason we can't is because the absolute value, it's actually a piecewise function kind of, in that this is really just y equals 1 plus x, and this is y equals 1 minus x. And this has an increasing slope. This has a first derivative of 1. This has a first derivative of negative 1. And so it has a second derivative of 0 in both cases. Okay. So this is a case where we have information about a graph, but a lot of our concavity discussion does not work because of some things being undefined. The first derivative up here does not exist because of the teeter-totter effect. All right. So what we can find is that, and in this one, by the way, it wanted us to limit ourselves from -1 to 1. So actually, these big green dots here would be our endpoints, because if you plug -1 or 1 in, you get 0. So let's look at our critical points. Our possible critical points are -1, 0, and 1, 0, because they are the endpoints, and then also 0, 1. Those are all critical points, and then we want to decide, are they absolute maxes or absolute mins? Okay, and so we take a look at the first derivative. The first derivative is undefined, okay, at x equals 0, and that's how we know that we have a critical point there. The second derivative of 0, if we plug that x equals 0 in, is 0, because the second derivative is always 0. And so that tells us that there's no concavity change, and so the fact that that is 0, that means it's not either concave up or concave down. So that doesn't help us. And so then what we do is we look at the graph, and we see that the endpoints are lower and that we have an absolute max at 0, 1. So that's not a pretty example for that reason, is sometimes we have to piece things together. The first derivative being undefined at x equals 0 does tell us we have a critical point. But the fact that our second derivative is 0 all of the time, what that is saying is that it's neither speeding up or slowing down in its change. Its change is consistent, and so that doesn't help us as much, and so then we look at a graph. But it's understanding all these things and being able to piece it together. In part 2, I go over a few examples that are a little more complicated to help you make connections, but the key thing is understanding, what does first derivative mean, what does second derivative mean, what does it mean to a company that's concave up, concave down, what's a point of inflection to a company. So really be thinking about this in terms of a profit graph or a revenue graph or that type of thing. Hope this helps a little bit, and please make sure to watch video part 2.